assign graphing review 2 to you? I can't remember. Okay, but we did graphing review 1, right?
Yes.
But I went over that. We talked about pretty much that whole thing, or did I go over some and then ask you to do the rest?
You went over some and had us finish it and then show you and then more time anything else.
And I didn't assign anything else. Perfect. All right, so if any of you missed that, that is in the grade book. So we'll take care of that. And then let's take a look at graphing review 2. All right. So for you guys, let's see. I just want to think of a few things we can hit upon. That's what I want to talk about. Okay, so this is not in your book. So I want to talk about the world of asymptotes. Okay, so there's 3 kinds of asymptotes. There's horizontal, there's vertical, and there's one that's called end behavior. Sometimes this is referred to as the slant asymptote. Okay, you don't really have to take notes on this. It's just kind of trying to get you dealing with and realizing where things can take place. All right, so a vertical asymptote is where the denominator is equal to 0. Okay, but something jumps in on vertical asymptotes called a hole. Okay, so a hole takes the place of an asymptote. So I want to show you first off what a hole looks like on Desmos. Okay, so going to our favorite website. Okay. Hey, Sammy's here. So, I just started, so you'll be able to catch up. All right, first. All right, so let's show what a hole is going to look like. Actually, I'm going to do this. I'm going to go y equals x plus 2 over x minus 3. Okay, so all I want to look at right now is the vertical asymptote. So friends, what number would I plug in to the bottom of the fraction that would make it a 0? What makes the bottom 0 on that? 3. Okay, so that means that I have a vertical asymptote at x equals 3. Okay? Okay, now I'm going to make a hole that's going to take place somewhere in our equation, and you can't really see a hole on Desmos unless you zoom in, and then it looks really bad. But before I do that, I'm going to zoom in just to an arbitrary place on this graph, really close. This is like doing a total microscope. Do you notice that my line is staying a nice line for right now? Like I've zoomed in pretty darn close to this. This is like, I can't even zoom in anymore. Okay, so that line stays straight the whole time. Does everyone agree with that? Okay, there's no interruption. It just takes place. So let's make it look like a hole. Okay. I'm going to go back to my numerator, and I'm going to type in x minus 3. Okay? So does everyone feel comfortable that this is a straight line? It appears to be a straight line. Agree? So in the world of math, the world of algebra, I have the same binomial on top and bottom. So right now, 3, if I plug it in the bottom, does give me a 0 on bottom, but if I plug 0 or 3 up on top, I get 3 plus 2 here is 5. 3 minus 3 is 0. I get 0 divided by 0, and 0 divided by 0 is undefined. Well, hello. We're talking about holes. What is this? Okay, so this graph does not have an asymptote. It actually has a hole. Okay, so the number that is the hole is the binomial on top and the binomial on bottom. The x minus 3 on top and the x minus 3 on bottom are the same exact binomial. Does that information make sense? So in the world of math, these cancel out. So let me show you. If those canceled out, that means that the next equation, if I canceled them out, would just be this. It's that green line. So notice, green line, red line, green line, red line. Look like the same thing. Agree? Exact same graph. Agree with me? Okay, so I'm going to keep that off, and I'm going to take a look at what is happening at x equals 3. So this is at 3. Notice on the bottom right there. So I'm going to just focus in as close as I possibly can get to this 3. Now remember when I did this last time, the line stayed a nice line, even though I zoomed in a whole bunch. Agree? So again, we're like acting like this is a microscope. Let's see what's going to happen if I get real close to this. It's not letting me get much closer. Now, what I want to do is this. Okay. Notice when I get to 3. What does it say? 3 comma undefined. So right there is an actual hole in this problem. So Desmos allowed me to zoom in much closer. What's really taking place is this line is coming from both sides like this, and at x equals 3, there's a hole. So it's undefined. A hole is not an asymptote. If it's an asymptote, the graph goes shooting up the side of it or down it, or both. But as far as a hole goes, that might take place. Now, I think there might be... Let's do this. No, I'm not. I just think it's no. That's not. This is not the one I want. I want to see. Is it going to let me? Folder expression table references folder image. I can't see a hole. Let's see anything here. No, done. Okay. So the big difference is at the value x equals 3. On my green line, it exists at 5. But if I go back here, we have it undefined. Okay? So that means there's a hole exactly there. So a hole will take place of a vertical asymptote. Now, a hole takes place when the binomial on top and on bottom are the same. Okay, so that's a vertical asymptote. So vertical asymptote can get superseded by something called a hole. Okay. All right, that's the first one. The next one I want to talk about is the end behavior. And this is when the degree on top is bigger than the bottom. Okay, so a slant asymptote is going to look something like this. Let's get rid of this. Let's get rid of this. Let's go y equals, let's go x raised to the third plus 2 or plus 2x to the second plus 5x plus 3. So if I go back and take a look at this, this is basically what that line's doing. You have one place that you have an actual answer or solution, which that's some decimal that I'm not sure what the fractional amount would be, but that's okay. So if I took this same equation and I went divided by, let's say I did divided by x. So this is kind of a wild graph. I could zoom out quite a bit, you know, and then you kind of lose it because you've gone way too far. All right. So what an end behavior asymptote is going to do is, as I'm going to the left on this line, there's something that another equation that I'm going really close to up this way. And when I come to the right of this line, I'm coming really close to this line as well. So there's basically some sort of equation that takes place, and it's called an end behavior asymptote. Okay? We will talk a little bit about those more later. Basically, our end behavior asymptote would look like this. 3x raised to the second plus 2x plus 5. Did I do that all right? Yeah, so this green line, if I come down here, this green line, as I go up, is going to get closer and closer and closer to the blue line. I don't know if it kind of looks like it yet or not. Does it appear that that green line is getting a little closer to the blue line on the left and the right side? So I'm up 3,600. If I keep going forever, that green line is going to get very, very close to the blue line both ways, which I graphed a parabola. So the end behavior of our parabola is going upward. Okay? And there's something we will do in order to show end behaviors a little bit later. But then the last one I want to talk about are the horizontal asymptotes. Okay? So degree on top is equal to the degree on bottom. You get, so if you had something like this, y equals 3x to the fifth plus big old thing over 7x to the fifth plus blah, blah, blah. This would have a horizontal asymptote at 3/7. So what you do in order to find this is you say, okay, I find my highest degree, which is 5. And then you look at the lead coefficient, and the lead coefficient over itself will be that. If in front of it, it's just x to the fifth on top and x to the fifth on bottom, then you get 1 over 1. 1 over 1 is 1. So that's one horizontal asymptote that would take place. Okay, so that's if the degree on top and the degree on bottom are equal to each other. The other horizontal asymptote takes place when you have the degree on top is less than degree on bottom. And that will always just get you the x-axis, or y equals 0. So if the degree on top and the degree on bottom are the same, or so if I made this, oops, let's make that raised to the 5th. Go back home. Okay. And this is a goofy looking graph, but the degree on top is 3, the degree on bottom is 5. That means that this x-axis, y equals 0, is the horizontal asymptote. So basically what's happening is this goes above the line and then comes back and it skirts along this line for a long, long period of time. It gets very, very close to the x-axis, never crosses it. And then this, as it comes down like this, it also approaches the x-axis. Eventually will try and get there, but it'll never get there. You could zoom in forever. If you could get a full table of values, you would see, and you went out, thousands and thousands of decimals, it would get very, very close to 0, but it wouldn't get there. So that's what, those are the 3 main asymptotes. Now, I didn't really hit the end behavior as much. That'll be something a little bit later for us. You have these domains. But, Starbucks gift card here. Got you. It's a $25 gift card for Starbucks. I don't know if it wasn't me. I promise, I'm just a messenger. All right, I want to focus on a couple of problems on the second page of Graphing Review 2. Go down to number 12. Okay, so what you need to know on number 12 is you have an equation that looks like this. Oops. Okay, this is called, from Algebra 1 or Algebra 2, this is called point slope. I have a point, which is x1 and y1, and I have a slope. And you literally just plug these in, and you don't have to, back in the days of Algebra 1, we made you actually solve it, but here all you do is you just plug in. So you get y minus 4, slope is 4/3, and then you have x minus minus 3. Minus minus means what? Plus. So this is the linear equation that contains the point -3 and 4, and it also has a slope of 4/3. You don't have to put that in slope-intercept form. You can leave it as point slope. Point slope is the more accepted way worldwide to do it. We here, water bottle right there, I licked it a few times. So this is more accepted, in business models and things like that. You don't have to do it as slope-intercept form. Slope-intercept form became very popular when the TI graphing calculators came out because they could only handle y equals. I could take this equation as it sits and plug it into Desmos exactly like that, and it's going to give me the exact equation. Okay? But then on the second one, I think an important thing to do is this is one that you want to use Desmos on. Not that you can't do it by hand. If you did that one in Algebra 1, you have to find the slope first, and then you use the point slope equation above it, and then you have to establish which one of your values is x1, y1. It actually doesn't matter which one you put in. They become equivalent things. But what I want you to get used to is look at 2 points as data. And if you use Desmos for this, basically what you do is you hit the plus on Desmos, you go down to the table, and you put your points in. So they gave us -2 comma 10 and -10. And then 1 comma -1. And if I could just take this out a little bit. Can you guys see your 2 points? Desmos will work this problem out for you, which is cool. Okay? And this is how Desmos works. We're going to use y equals mx plus b. You guys have used that equation before in some math class? So in the world of Desmos, my y value is y1. You just type y and then 1 right next to it. It becomes a subscript, and that's fine. Then you're going to use this little tilde button. If you can't find the tilde on your keypad, you look here, and if you go under functions, hello. Another Starbucks gift card. Best day ever. Gotcha. Thank you. So if you go and try and find tilde here, oh, actually, I know where tilde is at. It's under the ABC. Under ABC, it's at the very bottom row. You have this little tilde where my finger is. My head's probably in the way. So if you hit the tilde, tilde means you're telling Desmos you're going to look for equation. Then you go y mx1 plus b, and it gives you the linear equation right away. This will say, hey, y equals mx plus b. Yes, I use tilde. I use y1 and x1 because my variables up here were x1 and y1, so I had to use those to label it. So y equals 3x minus 4 is the equation to this line. So it's crossing the y-axis here at -4. If I go up 3, 1, 2, 3, right 1, you get right there. And it works out very nicely. So if I go up 1, 2, 3, right 1, 1, 2, 3, right 1. So it all works. So that tilde button is key. So if you're plugging data in, it can solve for you whatever the equation is. It doesn't just have to be a line. It could be a quadratic. It could be a cubic, quartic, quintic. Okay? So cubic third, raised to the third, quartic fourth, quintic fifth. Okay? That's the exponents. Now, it can also do if you had sine and cosine, if you plugged in data. An easy one to do if you had data ever given to you on, if you found out, if you went from January 1st to December 31st, and you plugged in 365 days, if it's not a leap year, of what time the sun set or what time the sun rose, and you're not taking into account daylight saving time, if you plotted it, it becomes a very nice sine or cosine curve. And it would solve for you the equation based on the sunsets, which is kind of crazy, or sunrises. So there's definitely some really powerful tools that Desmos will do. Why do we say, let's see, today is Thursday, agree? Why don't we, by Monday, have graphing review number 2 done? And then on Monday, we'll go over graphing review 3. Actually, I'm going to move our, no, it'll be okay. We'll after we get done with graphing review 3, then we'll go ahead and do the test, and you can do it together as a class, which I think that was kind of cool. And that's all I have for you. So graphing review number 2, have that done for Monday, because tomorrow, I think while we are on the ropes of the taxes, I think we want to still kind of hit upon a few things, because there's a few other places that taxes, you can lower your taxable income, which is what you want. And that's what we're going to do. Deal? Everyone happy? No one sad? And that's all I got for you.